Hello everyone. So today we're going to explore how the Pythagorean theorem is related to the geometric inequalities we learned about in the last lesson. So what we know currently about the Pythagorean theorem is that it tells us AC squared plus CB squared is equal to AB squared. This is the two legs of the triangle, the right triangle squared equals the hypotenuse squared. Now, we know that this is only true for right triangles. This is only true for right triangles. This is something we proved, I believe it was the first day we covered Pythagorean theorem. Now, let's examine the situation where this is not equal. So what happens if they were not equal to each other? Well, then we have two situations. We have that AC squared plus CB squared is less than AB squared. Or the other situation we could have is that AC squared plus CB squared is greater than AB squared. And what we're going to examine today is what is going to happen when we have these two situations. They can't be right triangles, but what kind of triangles could they be? So let's start with our first problem. Let angle C in triangle ABC be acute. Prove that AC squared plus BC squared is greater than AB squared. So let's draw our right triangle, or not right triangle, acute triangle, sorry. Just like this. We can make it a little bit more. Okay. And we will label the points. So we're going to have A, B, and C. And, well, look at what we are trying to prove. That AB squared, or AC squared plus BC squared is greater than AB squared. So that reminds us of the Pythagorean theorem, which again we know is related to right triangles. So we should form a right triangle in this problem. And we can easily do that by dropping the altitude at A to BC. Thus, we get a right triangle, and I'll label this point X. Okay, well, what can we do from here? Well, we can say that, how can I get something in terms of AB squared? Because this is something that's important in my problem. Well, AB squared is equal to BX squared plus AX squared. Now let's look at the two terms that AB squared is equal to. Let's look at BX squared. Well, because BX is a portion of the side BC, BX, we know, has to be strictly less than BC. So BX is strictly less than BC, which also implies that BX squared is less than BC squared. Okay, well now let's look at AX squared. Well, if we create another Pythagorean theorem, we have that AC squared is equal to XC squared plus AX squared. So what this here implies is that we know that XC has to be some positive value because it's a length of a triangle. So this cannot be 0, obviously. So AC squared is strictly greater than AX x squared. That's what this is all implying here. And let's put these two facts we have together. We know that bx squared is less than bc squared. And we have that ac squared is greater than ax squared. Well, if ab squared is equal to bx squared plus ax squared, well then that means that since bx is less than bc squared, less than, and ax squared is less than ac squared. And if we add those two together, that implies that ab squared has to be less than the sum of the two. So that completes our proof. We have proven that each term that ab squared is equal to is less than both ac squared and bc squared. Combining those facts together, we have that ab squared has to be less than bc squared plus ac squared. So we have shown that if we have the situation ac squared plus bc squared is greater than ab squared, then the angle at C must be acute. But when did we really use the fact that angle C was acute in this problem? We didn't really use that as a fact at all. Well, you'll kind of get to see this become important in the next problem, because assuming that angle C is acute, well, angle B is either acute or obtuse, and that's what's going to make the difference. So we'll see how that changes the outcome in the next problem.